And what?
Well, finally, we have in section 10.8 power transmission and the use of decibels in loss characterization. We know that the voltage, for example, in phasor form is like this. The alpha is positive, so the wave is decaying as it moves. So we also know the current is of the same form, and the amplitude is V0 over Z0, where Z0 is the characteristic impedance, and in the text it's given by Z is equal to the magnitude times a phase factor e to the j theta. So now we're all in a position to calculate the power transmitted down the line. And this is really our first application because there's no point having a transmission line if you can't get any power down it. So let's have a look. How do we define the time average power going down the line? Well, this is going back to circuits. So this becomes an exercise in complex numbers. Time average power that's deliverable is 1/2 the real part of what? Vs of z times Is of z conjugated. And that is equation 63 in Hayden-Buck. I've also edited it slightly to put in the z dependence. So power is flowing down the line. And now what we have to do is do the algebra, where you kind of get an idea of real fast what's going to happen. When we conjugate, this is going to knock that out, and these are going to double up. So intuitively, the power is going to go like e to the minus 2 alpha z with some constants. So let's check that out. So the power, and I'm going to say again, it's flowing down the line as a function of where we are, z. And so it's equal to 1/2. Just going to go to the second half of equation 64. It's going to be, you can check it out, V0 star divided by magnitude of Z0 e to the minus 2 alpha z times e to the j theta. So that's equal to what? Well, we forgot the real here, so let's put that in. The real part, what happens, of course, is this. These two cancel. This is in the denominator, so, and it's conjugated, so it's e to the minus j theta in the denominator, which is e to the j theta in the numerator. And of course, when we take the real part, all this is real. This is just going to give us cosine. So we get this nice final result, 1/2 V0 squared over Z0 e to the minus 2 alpha z times cosine theta. So this is the second step in Haight and Buck, equation 64. Final point is you can see that this stuff here, cos theta, and all of that is the value of the power when z is equal to 0, so e to the 0 is equal to 1. Now, what we can do is we can actually use this to start to think about how power is lost as we go down the line. And in the next board, you'll see what we do with this and introduce units of loss of power leading to decibels. Here we have the relationship we had before. P of z time average power is P of 0 times the exponential doubled up, e to the minus 2 alpha z, and that comes from the fact that it's basically the voltage squared. The voltage goes like e to the minus alpha z. Equation as given there from the text, and there's P0, that constant. Now, if we take the ratio of the two, we just got that exponential decay factor, which we like to write as powers of 10. That's equation 66. So we want to find out what k is, and the reason we want to use powers of 10 is because we're going to use the dB scale. So we need to find k, so we set alpha z equals to 1. Must be careful of the units. What are the units of z? It's a key point. Alpha has to have units of something, and we're going to call the something nepers per meter or nepers per meter. So nepers per meter times meter, that means alpha's a pure number. Let's put alpha z equal to 1 here. We get this relationship. And if we take the log to the base 10 of both sides, we solve for k, and we get the log of e squared to the base 10. E squared is about 9, so it's slightly less than 1, and there it is, 0.869. Now we define the power loss, which is loss, so it's going to be a positive number. 10 log to the base 10 of P0 over P of z, and with the scaling, it's 8.69 alpha z. That's in dB. So the conversion factor is this. So if alpha z is equal to 1 neper, which is this case here, we get how many dB? 8.69. So it's kind of a funny unit, but this thing is finally in what? In dB. 8.69 dB per neper. Then alpha nepers per meter. So you get dB over units of 8.69 alpha z is actually 8.69 dB per meter. Now, if alpha is per neper, it's easy to get mixed up here. Neper times, if alpha is 1 neper per meter, times 1 meter, and what's the power loss here? It's nepers cancel, meters cancel, and we get 8.69 dB power loss. And that's the key point in all this problem, is the units and the analysis. So 1 neper per meter at 1 meter converts to 8.69 dB. Hope that's clear.